Assalamualaikum and hi everyone. My name is Syahmi bin Azhar and my metric number is 20597. So today I will present about DSB, SC and SSB modulation and demodulation. So let's go. In this presentation, I will include about simulation and lab experiment for both the SSB, SC modulation and demodulation. So basically, DSB-SC modulation is a method where both the upper and lower sidebands of the modulating signals are transmitted, while the carrier is suppressed. In DSB-SC modulation, the message signal baseband signal is multiplied by the carrier signal to generate the DSB signal. The equation for DSB-SC modulation can be represented as this, and below this is its notation. Then, to demodulate the DSB-SC signal and retrieve the original message signal, the coherent modulation is typically used. DSB-SC signal is multiplied by the carrier signal again, which effectively shift the spectrum back to the baseband. The demodulation equation can be presented as this. And afterward, the demodulated signal may pass through a low-pass filter to remove high frequency components and then leaving behind the original message signal. And it is important to note that the DSB-SC modulation is not widely used in practical communication systems due to its inefficient use of power and bandwidth. More commonly used tend to include AM modulation with a suppressed carrier, which is SSB, or vestigial sideband modulation, VSB, that provide better spectral efficiency. Now, this is a block diagram that I have designed in MATLAB Simulink to simulate the DSB-SC modulation and its demodulation. So what we have now is, this is an analog filter design that I use, and also I set it as low pass 8th order Butterworth filter to ensure that the demodulation signal is generated as I expected. So this is an important component in this design because the low pass filter in the demodulators plays a vital role in recovering the original message signal and eliminating unwanted components. Because after demodulation, the DSB-SC signal still contains high frequency components resulting from the multiplication process. And the purpose of the low pass is to attenuate or remove these high frequency components, allowing only the baseband message signal to pass through. By filtering out the high frequency components, the low pass filter helps in reconstructing the original message signal accurately. And additionally, the low pass filter helps eliminate noise and interference that might have been picked up during transmission or introduced during the demodulation process. But for this design, I don't include noise. So the noise and interference is considered as negligible. Okay. So of course, I use scope to observe its output signal. So this is part of modulation, and this part, and after this part is the modulation part. So also I use a saturation block. So let's see what's the result. So this is the result that I get from the modulation part. This is audio signal, and this is carrier signal. And I forgot to mention that I have set for the audio signal is 300 millivolt of amplitude, and its frequency is 1 kilohertz. While the carrier signal I set 300 millivolt of amplitude also, but its frequency is higher, which is 100 kilohertz. So the parameter value that I use for audio signal and carrier signal is based on what I have used in practical lab. Okay, so now the result is the AM or the amplitude modulation from the DSB-SC modulation. So I want to remind again that DSB-SC or double sideband suppressed carrier modulation is a technique used in amplitude modulation that involves multiplying the message signal, which is the baseband signal, by the carrier signal to generate the DSB-SC signal. And the DSB-SC signal contains both upper and lower sideband, while the carrier itself is suppressed. Okay, the process of DSB signal modulation we can summarize as the first is the message signal is multiplied by the carrier signal using a mixer or multiplier. So in this case, I use multiplier, and then this multiplication results in the shifting of the message signal spectrum to both positive and negative frequencies, creating the upper and lower bands. And then the carrier signals, which is initially at a much higher frequency, is suppressed or removed from the modulated signal. Now, what we can see is a demodulation signal of the DSB-SC, and what I plot it as three layout or three output, because in the design, let me preview the slide. At the design, I plot for the first and the up at the top of the output signal is the signal that come out from analog filter design, and then the another signal is come up from the sum or multiplier, and then the other output signal is I plot from after the gain. Okay, so the demodulation of the DSB signal is to retrieve the original message signal, and coherent demodulation is typically employed because coherent demodulation requires the carrier signal in the demodulator to be in synchronization frequency phase with the carrier used in the modulator, and then the DSB-SC signal is multiplied again by the synchronized carrier signal, effectively shifting the spectrum back to the baseband. Afterward, a low pass filter, which is I use low pass 8 order butterworth filter used to remove high frequency components and leaving behind the original message signal. So what we can see is the signal is totally similar to the audio signal, which is the original signal. Now, this is SSB AM modulation that I have designed in MATLAB Simulink. So in the block diagram, you can see that I use a generator as to create the signal, input signal. And then I use also rate transition and SSB AM modulated passband to create a modulation. And then at the end of it, I use analog filter design again, which is I use also low pass at all the butterworth filter. And then I to generate to observe the output signal, I use scope. And as we can see the results, this is the top is the original signal, and the below is its SSB modulation signal. So as we know and as we can compare from the DSB, SSB modulation signal is usually have higher output amplitude than the SPSC modulation signal. So that we should know. Moving on to the practical lab experiment that I have implemented before. And this is the device that we use to generate DSB-SC and SSB modulation, which is SCT5. And as we can see, there are several potentiometer we have here to adjust the shape and also to lower the attenuation or the interference the signal. So here at the top is SSB output and the below is DSB-SC output. So let's see the result that I have get from this experiment. So this is the result of SSB amplitude modulations. So as we can see, the yellow one is the input and original signal, and the yellow and the green one and the green signal is a SSB modulations. So then we can compare with the DSB-SC modulations. As we can see here, DSB-SC modulation has significantly lower amplitude of output amplitude than SSB modulations. Now what we have here is SCT6 DSB-SC and SSB demodulators. This device is what we have used in physical lab to generate the DSB-SC and SSB demodulation signals. Actually, there are two types of demodulation signal, which are the product detector technique and the diode detector technique. So this one, this device, it applied the product detector technique since it has this balance demodulator MC1496 and also op-amp UA741. So let's learn how it works. So basically the first thing first, the SBSC modulation signal will fed into the input of this device, and then the MC1496 balance demodulator will take the DSB-SC signal and combine it with a local oscillator signal. And then the local oscillator signal is generated separately and usually has the same frequency as the carrier signal used during modulations. So the local oscillator signal is fed into the balance modulator, and then also there is mixing operations in the balance demodulator. The balance demodulator performs a mixing operation between the DSB-SC signal and the local oscillator signal. And this mixing process multiplies the two signals together, resulting in the generation of sum and difference frequencies. And then there is low pass filter. Following the balance demodulator, a low pass filter is typically employed to remove the higher frequency components, leaving behind the demodulated signal at the base band. And this filtering process helps eliminate any unwanted sum, frequency, and noise. And then there is UA741OM, used to amplify and shape the demodulated signal obtained from the low pass filter. And the OM helps to restore the original message signal by providing gain and buffering. So at the output of this SET6, uh, it will generate the DSB-SC or SSB uh, demodulation signals. So here is the result that we can get from the output of SCT6. And as we can see here, the yellow signal is the original input signal, and the green one is the output that we can get from the SCT6, which is the DSB-SC demodulation signal. So as we can see, uh, it's supposed to be both signal have similar amplitude and also phase and frequencies. However, due to attenuations or interference that occur during the experiment, especially it is due to the factor that the component that and the device that we use. So the green signal or the DSB-SC demodulation signal uh, has been affected with attenuations. So that's why its amplitude is considerably lower than it should be. So, in summary, the SBAC modulation allows the transmission of both sidebands while suppressing the carrier, while the SBAC demodulation involves multiplying the signal by a synchronized carrier and filtering out unwanted components. The SBAC is less efficient in terms of power and bandwidth utilization compared to other modulation techniques, but provides a simple way to transmit and recover the original message signal. In many communication application, to compare the SBSC and SSB, SSB is highly preferred because in SSB it has higher power concentration that make it more bandwidth efficient and suitable for many communication applications. So that's all from me. Thanks for watching.